Reality is overrated. In the next 10 minutes, we're going to go together in a tour. We're going to turn this on. We're going to go together on a tour. Shoot, that cost me 4 seconds already. Where's JR? JR, I'm sorry, we're going to have to cancel your interpretive dance. It's out, right out of the program. Let's take a tour through into the future where imagination trumps reality. I'm going to show you the illusion we're playing on robots throughout the cosmos that makes them the smartest entities this side of the Milky Way. Who'd have thought a trip to the land of make-believe would actually unlock the true power of computer vision? So I've got 1 minute, get out a timer. I've got 1 minute now to teach you everything I need you to know about machine learning. Okay, and if you're a machine learning expert and you know everything there is to know about machine learning and you couldn't possibly learn anything about machine learning, please just bear with us for this minute, help out your neighbor, and then maybe they can help you out later when we have the minute on how to talk to girls. Okay, traditional code. This is what we're used to. Traditional code, if, then, else, loops. When this happens, then we move to this. Think flowcharts. This is how we move through. In these conditions, when this happens, when that happens, then we are going to take this action. Machine learning doesn't work that way. We call it learning because it kind of seems like learning. It's analogous to learning. What we're going to do is we're going to just give it so much data, and then we're going to let it make inferences from that data. It's going to draw probabilities that probably give it the right answer out of that. So if we say wanted to create a earth-shattering computer vision model that could identify hot dogs, we would need lots of pictures of hot dogs. 10,000 maybe 100,000, maybe 1 million. And then something else important is we need to know what the hot dog is. So we need somebody to click on all the pictures of the hot dog, circle the hot dog. So Timmy has to look at 100,000 pictures of hot dogs. Timmy doesn't love his life. So there's got to be a better way, right? Okay, this is what we call training. And so we're going to get this training data and we're going to label that data. So what we've been finding in our research is that customers are telling us it's taking so long to obtain the training data. It takes us 3 weeks or maybe it takes us a year to take 100,000 pictures of hot dogs. The problem is, then it takes us about that same amount of time. It takes us another 3 weeks, so it takes us 6 weeks total to have the labeled pictures of hot dogs. Or if it took us a year, then it takes us a total of 2 years to get our labeled data. Reality has failed us for the last time. So there are all kinds of things with real data that are an issue. Maybe we don't have access to the environment. We'll talk about how that might happen in a minute. We might not have enough data. If there are only 2 hot dogs in the world, it's going to be difficult to get us enough pictures of the hot dogs. World shortage of hot dogs could be a problem for computer vision. We might need to generate diverse conditions. On and on it goes. 3D information, we'll dive into some of this. Ultimately, a chef is only as good as his ingredients. So if we can't give good enough training data, our model is not going to be that great. There's no way to take rotten tomatoes and make a great tomato sauce out of it. So a few of the things that we're running into with reality failing us. We talked to one customer and they said, we're doing kitchens, and in the kitchen we identify a toaster. Great, we're good at identifying toasters. You expect those in a kitchen. Cell phones in the kitchen, that's okay too, we can do that. But God forbid the cell phone touched the toaster, we're ruined. And so there's certain scenarios which you might want to create. Cell phone on the toaster, under the toaster, beside the toaster, toaster obscuring the cell phone. We humans pretty good at identifying sliver of cell phone and going, oh yeah, that's my cell phone, whatever. Computers, not that good unless we give them good training data. So if we can create training data that leans the cell phone up against the toaster, great. Other things that we run into, accurate 3D information. I can have the best picture in the world. How far is that pixel? Oh, maybe far. But if we create the training data, oh, it's 7.28124 meters. And I can tell you for every single pixel in that image how far away that is. If we look at labeling, and then we say, okay, well, we'll speed up our labeling by using AI to label the images. Wasn't there a Star Wars reference about the robots are creating the robots? So this is a little sus if we're going to let the robots determine this. We label it, this is an ugly, large dog. So maybe even worse than unlabeled data is incorrectly labeled data. But if we synthesize the data, not only do we recognize it's a giraffe, we can recognize where every point is. We could recognize the giraffe behind the grass. We know that those pixels, even though they're grass, behind them is giraffe. So we can get very precise with these things. Not enough objects, angles. Here's my rubber duck, but one rubber duck isn't enough. I want to see it in different environments. I want to see it at different angles. And so by creating the data, we can create all those things. And then take it further into stuff that we're just starting to do now, multimodal. What about infrared, LiDAR, audio, visual? Think about how we as humans process things. If you take one sense away from us, that's a big deal, right? We use multiple senses all the time. But then we think computer vision, we only give it, it's missing 4 senses. 5 if you have that other thing. But we inherently use the senses together, right? Like if something makes a sound, right? You heard the sound, you saw that thing go, you associated those together. So we might even train the things separately, and they don't have that ability to tie those things together. So multimodal, we let it recognize, what about smell? Really, we're gonna make robots smell? No, think about like CBRN, like chemical, biological, radiological, like all those different senses that we can actually use and bring into a robot. We can all of a sudden include all of those things. So a client came to us and they said, okay, we want to do an open world simulation for training a robot. So you think, okay, we're going to do open world, think like first person shooter, Call of Duty, that kind of thing, where I can go around anywhere. And you think, okay, the world's a big place. I could do the Atacama Desert. I could be under the ocean. I could be in the sky. I could be, what if it's not our world? What if it's a world we don't have great data on? So NASA said, look, what we want to do is we want to be able to make this robot navigate autonomously across Mars. All kinds of issues with space that are in my 12-minute presentation. But the short end of it is we want to be able to tell the robot, go to that edge of that crater, and I want you to do some science over there. But God forbid we miss signs of life on the way. So we're going to look for blueberries on Mars. Okay, blueberries on Mars are like grape nuts. It ain't grape and it ain't nuts. They're not blue and they're not berries. But they're these little sphericals of hematite. They're a high concentration of iron, and they tend to form in places where there may have been water before. We care because that's where we think there might have been life. So we're looking in those places. So if you see blueberries on Mars, either kind, you should stop and let us know. And so we're going to train a model to be able to recognize things on Mars. We don't have enough data for Mars. So we're going to create a synthetic Martian environment. Lots of bad things happen in the 14-minute presentation. You get the idea. Mars, very difficult. Okay, footage from Mars. We're going to pull in actual footage from Mars. So we have some of that from the rovers that are on Mars now. We're going to take scanned Earth objects that are really good models of rocks that look a lot like the rocks that we're seeing on Mars. And then we pull those together into a simulation. Now, to make that photo realistic, we've got to start adjusting things. Mars has a different atmosphere. They have about 1/100th of our atmosphere. We're going to have things that are super clean in the simulation. We might want to add noise. just continually adding things that make it more realistic. We might end up shifting the color because it's further from the sun. Things are different about the atmosphere. So we're going to apply all of those things so that we get more photorealistic data to train on. And then here's the really cool thing about synthetic data. Remember earlier we talked about you're going to spend half your life taking pictures of hot dogs and the other half circling the hot dogs. With synthetic data, when we create it, we automatically have the labels. So not only can we do the segmentation, so here are our blueberries. In this case, just to make the world more complete, we've made them blue. But we can also label every single thing. We can say every single rock I label separately. Depends on what our algorithm might need. We can do those sorts of things. We can also do depth. We can give, this is exactly how far this object is for me. Depends on what we need to do. So we take all of those things to give us automatic labeling, and we basically save half of the time on top of all the other stuff. In this process, we created a framework that we call Giraffe, which basically lets your robot exist in reality or exist in the simulation world, and your robot doesn't know the difference. It's like the movie Inception, but for your robot. In the 16-minute presentation, I cover that in more detail. Okay, questions? Thank you for that question. Yes, how do we figure out if this actually worked? How do I know if I did a good job with the data? How do you know that the synthetic data is accurate? Don't do that. You already have a way to know if your model is accurate. You're already doing something to benchmark your model to go, is the real data I'm putting into this giving me the results? Is the robot identifying blueberries? Are the percent likelihood that these are blueberries high enough? Can I make them higher? You're already doing all of that. So just apply the synthetic data, add it to your model, and then if it's better, then that's good synthetic data, and that's the synthetic data that you want, just like you would do with images, or okay, look, when I take more images this way, or when I don't add different lighting conditions, it doesn't make my model better. So apply, just like you would with your normal images, to the things that you're doing in in reality versus non. I'm losing myself in the Inception. Okay, everyone, that guy always has a follow-up question, which is, he has a follow-up question. What's his follow-up question? We were doing so good there. We're right on track. Go ahead.
Doesn't synthetic data cost something? And so trying synthetic data inherently has some risk of losing your money?
Yeah, there's going to be some cost maybe to generating it or putting together that simulation, that kind of thing. And you're going to weigh that against what's the cost of taking the 100,000 pictures of hot dogs. Also, if you really are just identifying giraffes, we got plenty of pictures of giraffes. You're probably fine with the data sets that are out there, right? It's the kind of things where we step into some of these others that are Mars. We don't have enough of the data. Or you have a brand new product and you've only got 2 pictures of it. That's enough, not enough data, but you need to train a model to recognize your product in the world or something. So these are situations, there's situations where it's cheaper to use synthetic data, or it's more accurate, or it will enhance the real data that you have now. And there's situations where you just cannot get the real data, so you're gonna have to do it. Car crashes where people die. Like, I'm sure it's gonna make your car way safer, but let's not kill 100,000 people to get better training data. Why don't we simulate that and get that from the simulation? So I will be happy to answer any questions you guys have out here. I'll cut off the next one. I'm Brian Geisel, CEO of Geisel Software. Thanks so much. I hope you guys felt like you learned something. If you did, please, follow the links. And if you'd like to follow me, this is what I look like from the back.